Unit 13, Superposition. What you have learned previously is about light travels in the straight lines. We use ray diagram, which is what we call geometry optics, to explain the image formed by a mirror, as well as the incident ray being reflected and transmitted. Now we are going to use waves. This branch of physics is called physical or wave optics, to explain spreading, which is the diffraction, as well as the interference of waves. We can't use ray diagram to explain this phenomena, so we use waves. As you can see here, when the wave passes through the gap between the two rocks, it starts to spread. Okay, similarly here also, and then you get interference pattern, as seen in the diagram. To understand the superposition of wave, we need to first study the principle of superposition, which is basically a formula that teaches you how to find the resultant wave displacement. So to find the resultant wave displacement, according to the principle of superposition, you just need to take the vectorial sum of the individual wave displacement. So let's take a look at the animation here. I'm going to pause it. So at this instant, right, at the position 10, you can see that the displacement of one pulse is here, the second pulse is here. So using the principle of superposition, I add these two together, I'll get the resultant displacement to be somewhere here. So likewise, you do it for all the positions where the two pulses overlap. Then you will get a resultant waveform like this. And this resultant waveform is obtained using the principle of superposition. If one of the pulses is negative, then we have to subtract because it's the vectorial sum. So we need to consider direction as well. Okay, one thing you must bear in mind when you want to apply the principle of superpositions, the waves must be of the same type. If it's sound waves and water waves, there will be no interference, or there is no superposition. Reflections and superpositions. Okay, if I have a pulse moving through a medium, it could be a pulse moving in a string, and the string is fixed at one end, say tied to the wall. Then you look at the animation, incident crest will be reflected 180 degree and you have a trough. So it's the opposite 180 degree reflection of the incident pulse. The reason for this is Newton's third law. Okay, say the medium here is a string. So when the pulse is approaching, it will actually exert an outward force at the fixed point. According to Newton's third law, the wall will exert an opposite force on the string. Since the rope exert or the string exert outward force on the wall will exert a downward force on the string. That's why the pulse get reflected 180 degrees. On the other hand, if you have a pulse moving through a medium which is free to move at one end, okay, say a string instead of tied to the wall is tied to a ring, and the ring is allowed to move up and down, then the incident crest still becomes a reflected crest, still remains as a crest, because there isn't an opposite force since the end is not fixed. In fact, if you look at the end, the reflected pulse and the incident pulse is superimposed. That's why the resultant amplitude, right, is 2 times that of the incident pulse. With that, let's take a look at example 1. Two pulses are traveling along a string in opposite directions as shown. If the wave velocity is 2 meters per second and the pulses are 6 cm apart, sketch the patterns after 10, 15 and 20 milliseconds. Okay, you can pause here for 5 minutes to answer this question. Okay, for part A, right, the time is 10 milliseconds. So I need to calculate the distance traveled by each pulse. It will be given by velocity times time. So each pulse will travel 2 cm. At t equals to 15 milliseconds, the distance traveled will be 3 cm using the same formula, velocity times time. So the two pulses will be meeting completely at this time, and the two pulses are identical. Therefore, at this instant, there will be cancellation of wave. According to the principle of superposition, the resultant wave will be just a horizontal line. At t equals to 20 milliseconds, the distance travelled by each pulse will be 4 cm, and therefore the pulse will look like what you see here. Okay, in part B, you are asked what has happened to the energy at t equals to 15 milliseconds. Well, at 15 milliseconds, we see that it's a second diagram, it's a horizontal line, so there is no pulse visible at that instant because of the cancellation. So we say that the energy is trapped within the wave. That's the end to section 1.